have Dr. Sofia Lorenzon speaker with us to talk about the Earth's deep mantle through those deep diamonds of the work that she and as well as the lab that she's working in or has been working in for a couple of years. That's a very unique sample, so that could provide us a glimpse into the Earth's deep mantle in terms of their composition as well as different bizarre minerals, so that could really broaden our understanding in the last 20, 30 years. So, Sophia, I think you could go ahead. I saw your second slide, so that was going to introduce yourself again. Okay. Normally we have to talk about 45 minutes, but we are a little bit flexible on that. And then please leave some time for interaction with our participants. And our participants today, as I could see, some of them working on natural samples, but I do see a couple of people working on very high pressure experiments. And they could also probe in the lower mantle too, and are very interested about your work. So for the rest of time, please, Sophia.
Okay, good evening to everyone. First of all, I want to thank you for inviting me to hold this seminar, in which, as Zanzu say, I will try to explain you the rule of diamonds and their importance in earth sciences. And in order to do that, I will present you the results that I obtaining during my PhD. Of which the title has been Peering into the Deep Earth Through Diamonds. So, but before to start with this presentation, I want to introduce myself. I am Sofia Lorenzon, I am Italian, and I have recently obtained my PhD in geosciences at the Department of Geosciences of the University of Padua. And in these last 4 years, I have worked with Professor Fabrizio Nestola and Professor Paolo Nimis. And my research has been focused on the study of inclusion diamond systems using in situ non-destructive analytical approaches in order to determine the genesis and the depth of formation of super deep diamonds and of particular special category of super deep diamonds, which are the ferropericles bearing diamonds. And subsequently, in the next slides, I will explain you why super deep diamonds are important in geosciences and why we were interested in the study of ferropericles bearing diamonds. So, in order to explain you all this stuff, I decided to divide this presentation in 4 different parts. And in the first part, I will explain you what are diamonds, why diamonds are important in geology, and which kind of information we can obtain from the study of diamonds. Subsequently, I will briefly present you the methods that people use at the University of Padua for studying diamonds. And finally, I will report 2 different examples where the main results of my PhD project are summarized. And in the first example, I will present you the results that have been recently published on an article on geology, and which title is Ringwoodite and Zirconia Inclusions Indicate Downward Travel of Super Deep Diamonds. Whereas in the second example, I will present you the results that I obtained about the genesis and the depth of formation of ferropericles bearing diamonds. So starting with the first part of this presentation, diamonds, what are diamonds? So as probably all of you know, diamonds are very precious and important minerals. But diamonds, in reality, are characterized by an extremely simple crystalline structure and an extremely simple chemistry. In fact, diamonds are the cubic high pressure polymorph of carbon. And despite this extreme simple chemistry and crystalline structure, diamonds are characterized by special chemical and physical properties. For example, the extreme hardness. In fact, diamonds are the hardest material that we have in our planet, practically. The high thermal conductivity, the high electrical resistance, and the high chemical stability. And thanks to these very special chemical and physical properties, diamonds are used in different fields of industry, but are also used as gemstones in the jewelry world. For example, diamonds are in fact used as abrasive or for building, cutting, and grinding tools. But diamonds are also used for constructing specialized tools used in different applications and also in research, for example. In fact, as you can see here in this picture, here is reported a diamond anvil cell. The diamond anvil cell is a tool used in experimental mineralogy for reproducing the high pressure conditions that we can have in the interior of our planet or in the interior of planets in general. Finally, diamonds, when they are extremely poor, are also very precious gemstone used in jewelry. And as you can see here, diamonds can be present in different colors, in yellow color, pink color, blue color, and rarest is the color of the diamonds, and most vivid is this color, and more expensive these diamonds will be, and more high will be their commercial value. So, but if diamonds are so important and so used in industry and jewelry, why diamonds are also so important in earth sciences and why are geologists so interested in the diamond study? Diamonds are extremely important samples because they are the only natural samples that we can find in Earth's surface able to give us geological information about the Earth's mantle. And this information can reach the depth of about 800 kilometers depth. Okay, but which kind of information we can obtain from the study of diamonds? These information are about the mineralogy of the Earth's mantle, the petrography, the geochemistry of the Earth's mantle, but are also information about the possible geological processes that can occur in our Earth mantle. And being diamonds carbon mineral, diamonds can also give us information about the carbon cycle within the Earth's mantle or the Earth's interior in general. And this information results extremely important because we can obtain this information alternatively only by performing high pressure and high temperature experiments or performing theoretical models or geophysical explorations. So, but which kind of diamonds are useful for us for obtaining this information about the Earth's mantle? In fact, diamonds that we can find in our Earth's surface can have different origin and different genesis. And as a function of this, we distinguish mantle-derived diamond, and as just the name say, these diamonds are important for us for studying the Earth's mantle. And these diamonds can be divided in monocrystalline diamonds, which are single crystal diamonds practically, and polycrystalline diamonds. Polycrystalline diamonds are diamonds characterized by an inner core made by a single crystal diamonds. And this single crystal diamonds is covered by a series of polycrystalline diamonds. And as a function of the shape of these polycrystalline diamonds, we can distinguish coated diamonds and fibrous diamonds. And interesting things is that usually the diamonds present in the core, the single crystal diamond present in the core of this sample is older respect the diamonds that are present in the coverage of this sample. So, but in addition to the mantle-derived diamonds in the Earth's surface, we can find also the so-called ultra-high pressure diamonds. And these diamonds are usually present as inclusions within garnets or other minerals that compose the metamorphic rocks in the mountain belts, but can also be present in the carbon layer that are always present in these metamorphic rocks. And the presence of these diamonds in these rocks is extremely important because indicate that these rocks underwent pressure conditions where diamonds are stable. And these pressure conditions are pressure conditions of a minimum of about 3.5 or 4 GPa. Finally, in our Earth surface, we can find diamonds not only in the terrestrial samples, but also in the extraterrestrial rocks or in meteorites in general. In fact, diamonds can be present in a particular type of meteorites, for example, and these meteorites are called Ureilite meteorites. And these meteorites are extremely similar to the peridotic rocks. And diamonds usually are associated to other carbon phases. And the origin of these diamonds in these samples are probably related to a very high impact shock that these samples underwent. So, by returning to the mantle-derived diamonds, in which way these diamonds form in the Earth's mantle. Probably, differently from some of you can think, diamonds in the Earth's mantle do not form for a direct conversion or a direct transformation from graphite or from another carbon phases. But diamonds in the Earth's mantle are the metasomatic product of reactions that occur between carbon-bearing fluids or malts and rocks present in the Earth's mantle. And this reaction can occur in a very huge depth range, which depth are from about 120 to at least 800 kilometers depth. And considering this very huge depth range at which diamonds can form, we divided diamonds as a function of their formation depth into different categories. And these categories are, in the first case, the lithospheric diamonds. And these diamonds form at the shallower depth in the Earth's mantle. And this depth is from about 120 and 220 kilometers depth in the mantle that are lithospheric mantle, and in particular these diamonds form in particular portions of mantle that are called mantle keels, and these mantle keels underlying the old and stable cratons that we have in our planet. In general, these diamonds present regular shapes, and these shapes can be octahedral or dodecahedral or a combination of these two morphologies. And lithospheric diamonds are the most common diamonds that we can find in our Earth's surface. In fact, they represent about the 99% of the worldwide diamond population. So on the other hand, the other group of diamonds are the so-called sublithospheric or super deep diamonds. And these diamonds are the objects of this presentation and of my research in general. And these samples can form at depths from about 300 to more than 800 kilometers depth. And they can form in the portions of the Earth's mantle that are the astenospheric upper mantle, the transition zone, or the lower mantle. And these samples result extremely important in geology because these are really the only natural samples that can give us information about these portions of the Earth's mantle. So differently from the lithospheric diamonds, sublithospheric or super deep diamonds present irregular shapes in general. And even if these diamonds are extremely important for Earth sciences, these diamonds are extremely rare. In fact, represent only the 1% of the worldwide diamond population. So, but arriving at this moment, I have a question for you. Are we sure that all mantle-derived diamonds that we can find in our Earth's surface are able to provide us information about the Earth's mantle? The answer is not. In fact, the most indicated samples for studying the Earth's mantle are the so-called inclusion-bearing diamonds. In fact, most of the geological information that we can have from diamonds are provided properly by fluid and mineral inclusions that diamonds can contain within them. Okay, but what are these inclusions? Inclusions are pieces of fluids or pieces of mineral different from diamonds, and this material can have different origin. In fact, in the first case, inclusions can be pieces of minerals or fluids that compose the mantle rocks present in the Earth's mantle, and these pieces of material were entrapped by diamonds during their formation in the Earth's mantle. And considering that this material is pre-existing material respect the diamond, we call these inclusions protogenetic inclusions. On the other hand, inclusions can also be pieces of fluids of pieces of minerals that form at the same time of their diamond host from the same metasomatic reactions. And considering that these materials form at the same time of their diamond host, we call these inclusions syngenetic. This distinction is extremely important because I will explain you better after in the next slides. Because knowing if inclusions are protogenetic or syngenetic allow us to understand which kind of information we can obtain from the study of inclusions within diamonds. So, as I just mentioned it before, these inclusions allow us to study the mineralogy, the petrography, and the geochemistry of the Earth's mantle, and also the geological processes that can occur in the Earth's mantle. But for constraining this information of the Earth's mantle, we need to know at which depth the inclusion diamond system form, and most important, which is the growth relationships that can exist between these inclusions and their diamond host. So knowing if inclusions are protogenetic or syngenetic. Okay, but in which way we can determine these two important information? So at the University of Padua, we try properly to determine the depth of formation and the possible growth relationships of inclusion diamond system using the so-called in situ, non-destructive, spectroscopic, and crystallographic analytical approaches. Okay, but first of all, why properly in situ non-destructive analytical approaches? So in situ non-destructive means that we are able to study the inclusions within diamonds without destroying the diamond's host and without extracting these inclusions from their host. And okay, this is very important for two different reasons. The first reason is that these techniques allow us to preserve the diamond samples. In fact, even if the diamonds used for research aims are not beautiful and they do not have the same commercial value of diamonds used in gemology or as gemstones in general, these samples are in any case diamonds. And for these reasons, it's better to preserve the original samples. And the other reasons, more important from a scientific point of view, is that if we preserve the sample, we are able to perform different kind of analytical techniques in the same samples, in order to obtain more information as possible from the same diamond. So the second reason for which we are interested in using in situ non-destructive analytical approaches is that in this way, if we preserve the inclusion diamond system, we can be able to study the possible growth relationship, or in general, the possible relationships that can exist between inclusions and their diamond's host. So, but which kind of in situ non-destructive analytical techniques people use at the University of Padua? So the in situ non-destructive analytical techniques are a lot. But at the University of Padua, and okay, for my research, I mainly use two different type of analytical techniques. And the first one is the micro-Raman spectroscopy. And here in this picture, you can see the micro-Raman spectrometer, that we have at the Department of Chemical Sciences of the University of Padua. And the second technique is the single crystal X-ray diffraction, the most important probably. And here in this picture, you can see the single crystal X-ray diffractometer that we have at the Department of Geosciences of the University of Padua. And as I will explain you subsequently, this is a special single crystal X-ray diffractometer properly built for study inclusions within host. So, but more in detail, micro-Raman spectroscopy. Okay, micro-Raman spectroscopy is a powerful analytical technique used in different fields of research. And this technique uses the interaction that we have between monochromatic radiation and material. And this interaction allows us to determine the vibrational modes of the molecules that compose the analyzed material. And into this space, we can visualize these vibrational modes in the so-called Raman spectrum. Here we have an example. And as you can see here, the Raman spectrum consists of a series of Raman peak or Raman band, and each Raman peak corresponds to a particular vibrational modes of the molecule that compose the analyzed material. And the Raman spectrum can be considered as a fingerprint of the material that we are analyzing. And for this reason, micro-Raman spectroscopy is used for the rapid identification of material, both amorphous and crystalline material. This is very important. And another important thing is that this method does not require a sample preparation. And in this way, for these reasons, we use micro-Raman spectroscopy and diamond inclusion study as a first step for the identification of both fluid and mineral inclusions that diamonds can contain within them. Okay, if we analyze the Raman spectrum of inclusions and also the Raman spectrum of diamonds, we can also other kind of information. But as the first step, this technique is used for the identification of the material. So continuing with passing to the single crystal X-ray diffraction, this technique, differently from the micro-Raman spectroscopy, uses the phenomenon of the diffraction, and this phenomenon is due to the interaction that we have between X-ray radiation and crystalline material. This is important because differently from the micro-Raman spectroscopy, single crystal X-ray diffraction or diffraction in general allow us to study only crystalline material. And the results that we have is, as in this example, a single crystal X-ray diffractogram. And as you can see here, we have a series of black spots, and these black spots correspond to the diffracted peaks that are the results that we have when during diffraction, a family of crystalline crystallographic planes in minerals enter in the diffraction condition according to the Bragg law. So from the indexing of this diffractogram, we are able to determine the unit cell parameters and the unit cell volumes of the mineral phases that we are analyzing. And this allows us to characterize these mineral phases and also to obtain information about the properties of this material. So as I just mentioned it before, at the University of Padua, we use a special single crystal X-ray diffractometer. And this special single crystal X-ray diffractometer is composed by a molybdenum X-ray microsource. A microsource because a microsource allows us to study very tiny material within an host. And the second important element that composes this single crystal X-ray diffractometer is the CCD detector, a very sensitive CCD detector that allow to this diffractometer to detect also the less weak diffracted peaks derived from the inclusions analyzed within the diamonds or within an host in general. So, but in the diamond study, in which way we use single crystal X-ray diffraction? Okay, single crystal X-ray diffraction is mainly used for two different applications. And the first application is the determination of the crystallographic orientation relationship that can exist between inclusions and their diamond host. And these crystallographic orientation relationships say as how inclusions are crystallographically oriented with respect to their diamond host. And this is possible through the determination of the UB matrices of inclusion and of the diamond. The UB matrices specify as is a parameter that specifies as how minerals is crystallographically oriented with respect to the reference system of the diffractometer. And this information is very important because allows us to understand and to determine which kind of growth relationships can exist between inclusions and their diamond hosts. So determine if inclusions are syngenetic or protogenetic. So The second important application of the single crystal X-ray diffraction is the application of the elastic geobarometry. The elastic geobarometry is a crystallographic method that allows us to determine the pressure and temperature entrapment conditions of an inclusion host system in general, knowing the so-called residual pressure and elastic properties of the mineral phases that compose the inclusion diamond system or inclusion host systems in general. Okay, but what are residual pressure and elastic properties? The residual pressure is the pressure exerted on a host, by a host, on the inclusion when the system is at room pressure and temperature conditions, whereas the elastic properties are the properties of the material expressed by the equations of states. And these properties say us how the volume cells of minerals changes as a function of pressure and temperature conditions. And combining these two elements, we are able to, through the elastic geobarometry, to determine and to calculate the so-called isomex. The isomex are PT curves in which each point corresponds to the PT conditions at which the volume of inclusions is equal to the volume of the cavity of the host that contain these inclusions. And in other words, the PT conditions at which the state of the residual pressure is equal to 0. And this is important because this point corresponds to the PT point at which the inclusion diamond system formed, the entrapment condition of this system. So, okay, I finished with this very brief presentation about the methods that we use at the University of Padua. And now we can start with the most interesting things of this presentation, that are the data and the results that I obtaining during my PhD. And I want to start with the first example that I report here. And this example is summarize the results that have been published recently on Geology about a work which title is Ringwoodite and Zirconia inclusions indicate downward travel of super deep diamonds. And this study results extremely important because Halu has to determine for the first time that diamonds after their formation in the Earth's mantle can also travel downward toward higher pressure and not only upward toward the surface as it was commonly assumed before this study. Okay, but we can start with this study, and I want to start with the initial aim of this study. In fact, at the beginning, the aim of this study has been to characterize for the first time a very beautiful and big alluvial diamond of 1.3 carats coming from Central African Republic. In fact, even if Central African Republic is one of the countries that produce the major amount of diamonds in the world, before to this study, anyone characterized the diamonds coming from Central African Republic. So we tried for the first time to determine if these diamonds are lithospheric or sublithospheric of both types. So, and to carry out this characterization, we perform mainly two different type of analytical techniques. And the first one has been the micro-Raman spectroscopy. And as I just said before, we use micro-Raman spectroscopy for the identification of the inclusions that we have in our sample. And the second analytical approach that we perform has been the secondary ion mass spectrometry. Okay, I didn't talk about this analytical technique because we usually do not perform this at the University of Padua. And in fact, these analyses were carried out in collaboration with the University of Lorraine in Nancy. And this method, this analytical technique allow us to determine the nitrogen content in our diamond. Nitrogen, in fact, is the main chemical impurity that we can have in the crystalline structure of the diamond. And the presence of nitrogen is very important to have information about the diamond formation. And through this analytical technique, we also determine the carbon and nitrogen isotopic composition of our diamond. And also this determination is very important because allow us to understand which is the possible carbon and nitrogen source of the diamond that we are studying. So, starting with the results that we are obtaining from the microRaman spectroscopy. The microRaman spectroscopy allows us to detect a very tiny and a very unusual multi-phase inclusions. That is the main results that we are obtaining in these study, sorry. And this multi-phase inclusion is composed by ringwoodite, tetragonal zirconia, and coesite. In this picture, in the green line, you can see the Raman spectrum of these multi-phase inclusions. But okay, we found these very unusual multi-phase inclusions. But why these multi-phase inclusions resulted important for us, and which kind of information we obtained by this particular multi-phase assemblage? So, start from the ringwoodite. Ringwoodite, probably, as some of you know, is a high-pressure polymorph of olivine. Olivine is a magnesium and iron silicate, and is the major mineral component of the upper earth mantle. And the ringwoodite is the polymorph of this mineral stable in the lower part of the transition zone, at depth between about 525 and 660 kilometers depth. And okay, probably most of you know ringwoodite because according to experiment, ringwoodite will be the major host of water in our Earth's mantle. So, but in our case, this ringwoodite resulted very important and resulted also only the second finding of these mineral phases within a natural diamond after the study of Pearson et al. In 2014. Okay, but in our case, the finding of ringwoodite, what say us? Okay, if we have a ringwoodite inclusion within our diamonds, this means that probably at some point of its history in the Earth's mantle, our diamond reside in the lower part of the transition zone where ringwoodite is stable. So, continuing with the tetragonal zirconia, this mineral phase is the high-pressure polymorph of badellite, which is zirconium oxide. And the presence of this mineral is in line with the presence of ringwoodite because this mineral phase can be stable at depth up to 20 GPa. Okay, but the finding of this mineral resulted important also because this was the first time that a natural tetragonal zirconia has found in a natural samples. Okay, and this in this case is an inclusion within a diamond. So finally, we found coesite in association with these two mineral phases. And coesite, as probably all of you know, is the high-pressure polymorph of quartz. And even if coesite is a extremely common mineral inclusions within diamonds, this is the first time that coesite is found in association with ringwoodite and tetragonal zirconia. However, the finding of tetragonal zirconia and coesite in contact each other in the same multi-phase inclusion lead us, considering the chemistry of these two mineral phases, this lead us to suppose that probably these two mineral phases are product of a reaction that at the beginning was a former mineral and this mineral probably was a zircon or a radite. The radite is the high pressure polymorph of zircon. So, and to understand this better, we analyze the pressure and temperature stability graph of zircon. And we observe that if we increase the pressure, zircon will transform in radite at the pressure condition of about 911 GPa, which correspond to 270 or 330 kilometers depth if we follow the subduction or the mantle geotherm. But more important, if we increase more the pressure, radite will transform in orthorhombic zirconia plus stishovite at depth of about 18 GPa and 20.5 GPa, which correspond to a depth of about 550 and 610 kilometers. And if we consider that woselite will transform in ringwoodite at depth of about 525 kilometers, these things suggest us that probably the multi-phase inclusion that we observe in our diamond is the result of a progressive transformation of a former inclusion composed by olivine or woselite plus zircon and radite. And okay, even if some of you can ask, okay, but how it is possible that olivine is in association with zircon? Because usually zircons do not crystallize in ultramafic rocks. Okay, this association can be possible because even if rarely, in literature, some example of presence of zircon in peridotitic rocks are reported, and zircons are explained as the metasomatic product precipitating by a zirconium-enriched fluid or as xenocrete mineral with a crustal origin transport in the peridotitic rocks by fluids or melts with also crustal origin. And the other important thing is that we suppose that this reaction occurred within the diamonds because probably if these reactions occur outside of a diamond shell, we didn't have the preservation of the ringwoodite and the high pressure polymorph of silica, because probably the high temperature conditions lead to ringwoodite and silica to react together to form a chemotoid. So continuing with the data that we obtaining from the secondary ion mass spectrometry, we obtained that our diamond has a low nitrogen content, a carbon isotopic composition quite negative, and a nitrogen isotopic composition quite positive. And okay, what means this? The fact that our diamond has a low nitrogen content suggests that probably this is a super deep diamond. In fact, typically super deep diamonds do not contain nitrogen or have a very low nitrogen content, as in this case. And the carbon and nitrogen isotopic compositions, on the other hand, are not similar to the isotopic compositions of the Earth's mantle, but are similar to the carbon and nitrogen isotopic composition of the carbonates and the clay minerals that are present in sediments. And for these reasons, we suppose that probably our diamond is a super deep diamond and precipitating from a fluid or a melt with a slab-derived origin. So, okay, all this information are extremely interesting for us. And in this way, we try to put together all of this information and we try to reconstruct the possible history of the studied diamonds in the Earth's mantle. And considering the fact that our diamond is a super deep diamond, we suppose that probably our diamond precipitate in a depth range between about 300 kilometers, with the minimum depth of formation for super deep diamonds, sorry, and a depth of about 550 or 610 kilometers, which is the depth at which radite will transform in stishovite plus orthorhombic zirconia. And during its precipitation, this diamond entrapped a former inclusion composed by olivine or wazelite plus zircon or radite. Subsequently, this diamond, traveled downward toward higher pressure, probably following the subduction, and this diamond reached the lower parts of the transition zone, where the former inclusions composed by olivine or wazelite plus zircon or radite re-equilibrate in a new one composed by ringwoodite plus orthorhombic zirconia and stishovite. Finally, this diamond traveled upward, probably transported by superfast kimberlitic magmas, and during the travel, the original orthorhombic zirconia and stishovite back transform in tetragonal zirconia and coesite. So, in conclusion, what we obtained by this study? Okay, this study and the finding of this very special multi-phase inclusion allow us to determine for the first time that diamonds, after their formation, can also travel downward in the Earth's mantle. And this in order of the possible implication about this important result is that, okay, this information could have important implication about the type of information that we can obtain from the study of inclusion within diamonds and about diamond formation. And another important implication is about the role of diamonds in the recycling of material in the Earth's mantle. So, okay, I conclude with this example, and now very briefly I will present you the second example, where I report the data that I obtained about the genesis and the depth of formation of ferropericlase bearing diamonds. And okay, starting with the aim of this study, the initial aim has been to determine the possible genetic processes and the possible depth of formation of ferropericlase bearing diamonds using methods that do not consider the mineral paragenesis of the inclusions within diamonds. So we try to understand in which way and at which depth the ferropericlase bearing diamonds form in the Earth's mantle without consider the other mineral inclusions present in the diamond. So, but first to start with the results, why properly we are interested in the study of ferropericlase bearing diamonds. So ferropericlase is an extreme simple mineral. In fact, ferropericlase is an iron and magnesium oxide. But ferropericlase is the most abundant mineral inclusion within super deep diamonds. But exist some discrepancies between the data that we have from the experiments about the mineralogy of the Earth's interior and data that we have from the study of natural inclusion within diamonds about the ferropericlase. In fact, if we consider the experiments, starting to a pyrolytic bulk composition of the Earth, ferropericlase result the second abundant mineral phases stable in the lower mantle at depth between about 660 and 2,900 kilometers depth. And this mineral is in association with bridgemanite and calcium perovskite. And the chemical composition of this ferropericlase will be magnesium rich, having value of iron index between about 0.10 and 0.27. On the other hand, however, from the study of natural inclusions within diamonds, ferropericlase results the most abundant mineral inclusion within super deep diamonds, representing about the 56% of total inclusions. But most important things, the chemical composition of natural ferropericlases is more variable respect the chemical composition of the synthetic ferropericlases. And their chemistry can also be very iron rich with value of iron index that can reach a value of 0.64. So even if in last decades different theories have been supposed to explain these discrepancies and the possible origin of iron rich ferropericlase inclusions within diamonds, so far we are sure that diamonds containing ferropericlases form in the lower mantle only when ferropericlases is associated to low nickel ansatite inclusions, because low nickel ansatite inclusions are considered the back transformation product of bridgemanite. But if ferropericlase inclusions ferropericlase is present as single inclusion within diamonds, considering that ferropericlase can be stable also at depth shallower than the lower mantle, we are not able to determine at which depth this diamond form and through which genetic processes in the Earth's mantle. So, for trying to understand this, in this study, we tried to determine the possible growth relationships that can exist between ferropericlases and diamonds in order to understand the possible genetic processes, determining, as I explained before, the crystallographic orientation relationships between these two mineral phases. And this determination was being between 57 ferropericlase inclusion and 37 diamonds. And these diamonds coming from both Juína in Brazil and Cancan in Guinea. And for the depth of formation, on the other hand, we apply the elastic geobarometry on only two ferropericlase-bearing diamonds coming from Juína in Brazil to determine their possible pressure and temperature conditions. So, starting from the data that we obtained about the crystallographic orientation relationships, we observed that ferropericlases and diamonds can develop different type of cores. And these cores are specific cores, and this means that the three main crystallographic axes of diamonds are oriented with the three main crystallographic axes of the ferropericlases. In some cases, ferropericlases can develop rotational statistical cores, and this means that one crystallographic axis of diamond is fixed to one crystallographic axis of ferropericlase. And finally, in some cases, ferropericlases can show random cores, and it means that no crystallographic axis of ferropericlase are oriented with any crystallographic axis of the diamond. So, but what means this in order of genetic processes? Okay, the development of different cores can suggest us that probably ferropericlases and diamonds interacted in different ways when the ferropericlase bearing diamonds form, and specific core can suggest us, for example, that during the formation of the ferropericlase diamond system, the two minerals interact through a surface interaction in order for minimizing their interface energy. On the other hand, the presence of rotational statistical cores can suggest, has also in this case, a surface interaction, but can also suggest as a possible mechanical interaction. But in our case, we exclude this possibility because for having this kind of interaction, we must have very well-developed crystals. Finally, the random core can suggest us that probably any kind of interaction occur during the formation of ferropericlase-bearing diamonds. So, but different kind of interaction. Which kind of information can give us about the formation of this system? So, in a very simple way, we can think that probably when we have a type of interaction, the inclusions are syngenetic. On the other hand, when we don't have interaction, the inclusions are protogenetic. But are we sure that in case of ferropericlase, this information is enough to understand this? Unfortunately, the answer is not, because for ferropericlase diamond system, in this moment, we don't have an ab initio calculation that allow us to predict how ferropericlases and diamonds interact for minimizing the interface energy. But considering that ferropericlases within diamonds, ferropericlase inclusions can present very different chemical compositions, this thing leads us to suppose that, okay, probably the development of different type of cores between two minerals can be correlated to the chemistry of these minerals. And in order to understand this, we determine the chemical composition of some ferropericlase inclusions that we analyze for the core determination. And we obtain that the iron-rich ferropericlase inclusion present in most cases specific cores. Okay, only one case is present random core. On the other hand, the magnesium-rich ferropericlase inclusions present in all cases random cores. And this leads us to suppose that probably ferropericlase inclusions within diamonds with different chemistry can have different origin in the Earth's mantle. And consequently, finally, we suppose two different formation scenarios for ferropericlase-bearing diamonds in the Earth's mantle. And the first is that probably the iron-rich ferropericlase inclusions within diamonds simultaneously precipitated with their diamond host at the depth of the lower part of the upper mantle or of the transition zone. Okay, this conclusion is related to the experimental results that Thompson et al. Obtained in the 2016, where Thompson et al. Predicted that probably iron-rich ferropericlases, with variable chemical composition precipitate simultaneously to their diamond host at depth of the lower upper mantle or of the transition zone. And on the other hand, conversely, the magnesium-rich ferropericlase inclusions are pre-existing mineral, rock-forming mineral, dissolved and trapped by the diamonds during their formation in the lower mantle. And this because the chemistry of these ferropericlase inclusions is similar to the chemistry of ferropericlase predicted by the experiments. So finally, I almost finished. About depth of formation, the results from two different ferropericlase-bearing diamonds say us that one of these samples form at a minimum depth of about 468 kilometers, whereas the second one formed at a depth of about 492 kilometers. And these formation depths are extremely similar and corresponds to a depth in the transition zone. And this suggests that probably ferropericlase-bearing diamonds can also form at different depth and shallower depth respect the lower mantle. And this thing is also suggested and supported by the previous data. So in conclusion, from the study of the ferropericlase-bearing diamonds, we obtain that probably ferropericlase inclusions with different chemistry have different origin as a function of their iron-rich nature or magnesium-rich nature. And we obtain also that these two information are also supported by the elastic gel barometry, where we obtain that probably ferropericlase-bearing diamonds can also form at shallower depth respect the lower mantle. So this is the last slide. I want to thank you again for the attention. And if you have questions, I'm ready to respond.
Okay, thank you very much, Sofia, for your talk. Now it's time for questions from participants. So feel free to open your ask question or leave me a question in the chat, and I could ask a question on your behalf. So first question, Lei from Zhejiang University, please go ahead. And then Renbiao could be the second one. Okay, I could not hear anything from. Like...
No, I
Hello?
don't hear. Okay, there is the chat here. Sorry.
But that's okay.
Okay,
I think Renbiao could go first. So Renbiao, please. You can go ahead.
Thank you.
Okay, I'm reading the question on the chat.
Okay,
okay.
maybe you have
Okay.
question. Yeah.
Okay, so I'm going to read a question, and then Renbiao's question could be the second.
Okay, no problem.
Okay, thank you. So Lei has two questions. First, it's about the phase transformation. It's radiate zircon decompose into zirconia and stishovite. Is it that easy to occur?
Okay. Okay, I respond to the first question. And okay, we don't know if this reaction is easy to occur, because unfortunately, okay, exist experiments about this reaction, okay, about the transformation phase from zircon, radite, and then high pressure silica and high pressure zirconia, so the orthorhombic zirconia and stishovite. But unfortunately, we don't have the cinetic of this reaction. And for considering what we have observed from the multiphase inclusion in our diamond, we suppose this, but at the moment we don't have data from a cinetical point of view. Also because also for the ringwoodite, so we must consider that we have also ringwoodite between these two mineral phases. But probably the conclusion, because at the beginning, according to the experiments, radite decomposes in orthorhombic zirconia and in stishovite, but we observe coesite and tetragonal zirconia. And okay, we know that the transformation stishovite coesite is extremely fast. In fact, never find stishovite in our Earth surface in any natural sample. But we don't know what is the reaction orthorhombic zirconia, tetragonal zirconia. But considering what we observe, we probably suppose that also this reaction is extremely fast, and probably is less faster respect the reaction ringwoodite wasselite or ringwoodite olivine. Okay, and the second question is, we know diamond is very, okay. Okay, also this question is extremely interesting. Okay, we don't calculated the pressure that arrive at our inclusion, also because we must consider that the diamond samples that we studied, here, okay, this is picture, okay, okay. So this is the diamond sample, and this diamond is extremely huge because the longest size, the longest dimension, sorry, of this diamond is 1 centimeter. And consider that this is not the original shape. The original shape was extremely irregular, but we cut the diamond because at the beginning we were not able to study the inclusion with the diamonds, because we have probably thicker layer of diamond for studying the inclusion with micro-Raman spectroscopy. Okay, with single, for example, with single crystal, X-ray diffraction has been impossible to study inclusion in this very big diamond. And the inclusion, our multi-phase inclusion, is extremely tiny, is about 7-8 micron. Multi-phase inclusion is this one. And we don't know perfectly at which depth in the diamond this inclusion is located. And we not calculate the internal pressure, but absolutely, probably diamonds exert, a pressure on this inclusion. And this is probably the pressure exerted by diamond on this inclusion allow the preservation of this new assemblage and the preservation of the ringwoodite. I respond to the question. Is okay?
Okay. Let's move to the second one. So okay, Professor Tarambia, please go ahead.
Thank you. Hi, Sofia. This is Ren Tao. Your talk is really impressive. I like your talk very much. So can you just move the slide to the Raman spectrum for your inclusions? Okay, I just wonder one thing is, do you think is there any residue pressure for your inclusion? The question is like in compare with the standard, right? So for the ringwoodite, you have two typical Raman peak. One shift to the high frequency and one shift to low frequency. How can you explain this? And one more question is for the coesite. You see there is some there is a Raman shift from standard. The standard coefficient is 5 to 1, but in your inclusion is 537. That means there are some residue pressure. You try to estimate the residue pressure. And one more thing following the next question is, I think because you have the rule that why you found the coefficient instead of the Geology? That's my question. Yeah, thank you.
Okay, perfect. Okay, the questions is I good understand is about the position of the Raman peak of our multi-phase inclusion. Yes, sorry, the Raman spectrum. Sorry, of our multi-phase inclusion and the position of the peaks of the Raman spectra of the standard, right?
Yeah. So you compare with the rule that. So
yes.
For your inclusion, the one peak shift to the low frequency and the one peak shift to the high frequency, right? So I just wonder why.
Yes. Okay. Allora, about sorry. So, allora is in Italian. Sorry. About the Ringwoodite. Okay. This Raman peak, this Ringwoodite is probably the Ringwoodite more similar, to a synthetic Ringwoodite. In fact, if you observe the Raman spectrum or the Raman spectrum of the Ringwoodite found by Pierce in the 2014, the Raman peak of the natural sample were shifted to higher wave numbers, to our Raman shift value. And this is because the position of the Raman peaks depend, on the vibration modes of the molecules that compose our material. But these vibrational modes depends of a lot of factors, the chemistry, the internal pressure, and a lot of things, and a lot of other parameters. And if we consider that we are studying a mineral that is not a pure chemistry mineral, but is a solid solution, because we have a silicate that can contain magnesium and iron, and the amount of magnesium and iron, is similar in general, is extremely similar for olivine, for wazelite, for probably also for Ringwoodite, but this composition can be different from a synthetic Ringwoodite. And also the condition.
You polish your sample, right? You haven't polish your sample and analyze the chemical composition. So maybe your composition is the evidence for that. Right?
Exactly. And the same thing is for the tetragonal zirconia. But for tetragonal zirconia is most interesting, this thing, because I don't know, probably some of you know that tetragonal zirconia is a synthetic mineral phase used for different applications. As a function of the application of the tetragonal zirconia, the people synthesize tetragonal zirconia with different chemical impurities, and as a function of this, the Raman spectrum changes. But before this finding, we didn't have any natural example of tetragonal zirconia, and consequently we didn't have any example of Raman spectrum of a natural tetragonal zirconia to compare with our diamond. And in addition, we must consider that we have, the tetragonal zirconia is the most probable phases present in this multi-phase inclusion. But tetragonal zirconia is probably a back transform product respect orthonomic zirconia, and we cannot know how this thing influence the reaction influence the position of the Raman peak. And finally, about the coesite, yes, we know very well that our coesite peak is broader and is also shifted to a very high Raman shift respect the Raman spectrum of the standard coesite. But this shift is possible because if we consider the presence of coesite, okay, coesite is a common inclusion within diamonds. And if we consider the Raman spectra of these inclusions, the Raman shift can reach a value of 540 centimeters at the -1. So the shift can be extremely high. And okay, in some cases, people use this shift for calculate the residual pressure exerted on diamond by coesite. But okay, in our case, we think that for this very high Raman shift, the result is not, we cannot have a probable result, I don't know, a right result, because we cannot know the anisotropic, okay, this thing is, this pressure can be also anisotropic pressure, and we cannot know how the anisotropic properties cannot change the Raman shift of this spectrum. So we didn't calculate this because probably okay, we calculate this, but we cannot consider this result as a good result to consider for our study.
Yeah, because from your data, you say for the zirconia and for the coesite, both data are shifted to the frequency, right? They are very consistent, right?
Yes.
Yeah, I think they may represent some residue pressure, right? Residue pressure. So yeah, that's my suggestion. Yeah.
Yes, but probably there exists a residual pressure. This inclusion is under a condition residual pressure, but for this particular case of multi-phase inclusions, we must consider different parameters, too much parameters, and the combination of these parameters probably don't allow us to obtain real results about the internal pressure. Also because we don't know if there is crack around the inclusion, because this crack lead to a loss of the residual pressure. And considering the amount of inclusions, it is too much inclusion within this diamond, and extremely big size of this diamond, for understanding this thing, we must perform the micro X-ray tomography. I don't know if you don't know this analytical technique. Okay, it's an analytical technique that allows us to reconstruct a 3D images of a natural sample, and in case of diamond, allows us to reconstruct the diamond and the position of all the inclusions that is present on the diamond. And this technique allows us also to determine the presence of fracture around inclusions. And the presence of this fracture is very important for also for the elastic geobarometry, for understanding if we have a release of pressure. But in this case, it's impossible to perform analytical technique. So, okay, it's possible, but we cannot obtain.
Okay, yeah, I understand. Yeah, very good work. So one more question. Question is very interesting. I just wonder, and I just want to understand more. So your zirconia is kind of crushed mineral, right? Right, it's kind of from the surface mineral, but the ringwoodite is represents the mantle mineral. So your inclusion looks like kind of cross mantle interaction represented, right? I just wondering, do you have the age for the data?
Yeah. Okay. At now yes, now in this moment, we were not able to determine the age of this diamond, even if there is a zirconia phase, because for this kind of determination, we must extract the inclusion for the analysis. And considering that this inclusion is extremely tiny, we prefer to not try to extract these inclusions, because probably we lose the inclusion. And okay, so far the instrument.
You are zirconia, right?
Yeah, probably in, okay, I don't know.
Use nano film
20,
like that. Data your zirconia. Yeah. Then
exactly.
you will have very good story.
Also, I think this, but I don't know if in the future we will be able to obtain this information without destroying diamonds. Probably we will try to determine the age of this inclusion diamond system.
Okay, thank you very much. Very good story. Thank you. Bye bye.
Thank you.
Okay, so there's another question from Lei about the nitrogen content. That your nitrogen content is consistent with other super deep diamonds that are low. You assume the diamond goes through a downward process. So this process will induce the variation of the nitrogen contents with carbon isotopes.
Okay.
So how do you explain that? Especially with your carbon isotope is homogeneous.
Okay. And the carbon and nitrogen isotopic composition, we obtain that the nitrogen present in the diamond the content of nitrogen is extremely low. And as I say in my presentation, we suppose that this diamond is a super deep diamond because in generally super deep diamonds do not contain nitrogen, or the amount is extremely low, whereas the lithospheric diamonds contain a huge amount of nitrogen in the order of hundreds of ppm. And for these reasons, we say, okay, probably our diamond is a super diamond. But as I say here, for these reasons, considering that super deep diamonds can form from about 300 kilometers depth and at least 800 kilometers depth, we cannot know the right depth at which these diamonds form. But considering that we think that it is probably a super deep diamond, and we also suggest that, and we also say that, our multi-phase inclusion is the product of a prograde transformation occur within the diamond. We suggest a possible depth range of formation. We cannot determine precisely at which depth, but we determine a depth range between about 300 kilometers, which is the minimum depth for super deep diamonds, and 550 and 610 kilometers depth, which are the depth at which radite would transform in zirconia plus silica. And at which depth, in this depth range, can be stable olivine and olivine wasylite, xenon, and radite. And in this way, we cannot determine perfectly which was the former inclusions that our diamonds entrapped. But we suppose that probably is this entrapment, occur at this depth range and entrapped one of these four mineral phases. And about the chemical composition, the carbon and nitrogen isotopic composition, yes, the carbon isotopic composition is quite homogeneous in the diamond, whereas the determination of nitrogen isotopic composition were more difficult, because if we have very low nitrogen content in our diamond, it's difficult to determine also the nitrogen isotopic composition. But all the significant results positive. And you say is homogeneous, but for us it's not a problem, because we say that probably this diamond form at certain depth and subsequently traveled downward, but during this travel probably this diamond did not precipitate another layer of diamonds Okay, he reached the transition zone, but at the condition of the transition zone, these diamonds stay in the transition zone, and the new inclusion are equilibrate, and subsequently these diamonds return in the Earth's surface toward the kimberlitic magma. Is it okay? Okay.
Actually, I have a quick question. Probably you have tried to analyze the water content of your ringwoodite. I think that could also be another way to trying to figure out that whether they're dry or not. If they're dry, then that could likely the samples trapped from the upper mantle and then sent to the deeper part. If not, likely that they're formed below 410 and brought to your current depth. But I suppose the samples are too small for you to move forward with that, I suppose.
Sorry, can you repeat that?
The water content of the ringwoodite.
The water content, sorry. Okay, the water content is a very good question. At the beginning of this study, when I found ringwoodite, okay, the first thing that me and other people that collaborated with me think is was ringwoodite, we absolutely must try to determine the water content of this ringwoodite. But the problem of these inclusions is that is too small, and the best way for calculating the water content is the FTIR analysis, as you probably know. But performing FTIR analysis on an inclusion so small and so deep within the diamond is not easy, also because the thick of the infrared ray is not small enough for studying a small inclusion such this one. But we try to determine the water content through the micro-Raman spectroscopy, because you know that micro-Raman and FTIR are complementary analytical technique, but FTIR is more sensitive to the vibrational modes of the water. Okay, we try also with the Raman spectrum, but we didn't obtain good results. Okay, these are results, but not supported results. And also for this kind of determination, if in the future we will have very sensitive FTIR instrument, probably we try to calculate and determine the water content in a very so small inclusions in this very big diamond. But the aim of this study was not to determine the water content, because it was quite impossible.
Okay, I think that's about it. Could you stop sharing your screen, Sofia? Everyone, could you open your video and show your appreciation for our speaker today?
Okay, sorry, one moment. Okay. No. Okay.
Okay. Let's see everyone, and then we are going to end the meeting in 30 seconds.
Okay, thank you.
Again, Sofia.
Thank you. Bye-bye.